Good morning, everybody, and welcome back to More Knowledge with Mr. Stewart. So, look, today we're going to start the second half of Chapter 6, which is going to be about equilibrium. So the first half is all about, like, what makes reactions happen, why, what can we do to speed them up, all that kind of stuff. And that all comes together to talk about this thing that we call equilibrium. So, look, here's the deal. This is how equilibrium sort of works, like, in a nutshell. You've got, like, a forward reaction, right? So let's say you have like this many reactants, you have 0 products, right? So as the reaction goes, the reactants get less and less and less and less, and then products get more and more and more and more and more, right? Well, let's think about this for a second. If you have a reaction that is reversible, that can, like, where the products collide and make the activated complex and then snap back together to make the activated complex, then, like, you got a reversible reaction, right? So it can go forwards and it can go backwards. All right, so that's kind of a thing. So if it can go both forwards and backwards, then as the forward reaction is going and the amount of reactants gets less and less and less, that means that the concentration of the reactants is going to get less and less. And we learned that, like, concentration affects the rate or the speed of the reaction, right? So as you get less and less and less and less reactants, right, as, like, the reactants drop, that means that the forward reaction is going to get slower and slower and slower and slower. Now, same thing, only the other direction. As the forward reaction goes and goes and goes, the amount of products gets more and more and more and more and more. So you're having more and more and more products. And as you get more and more products, that means that the concentration of the products is, like, going up, right? So as the concentration of the products goes up and up and up, that means that the rate of the reverse reaction is going to get faster and faster until the forward reaction slows down and the reverse reaction speeds up. So they're the exact same rate, or they're going the exact same speed. And if they're going the exact same speed, that means that one can't, like, outdo the other, and they get locked. So let me say that again. The forward reaction, or I'm sorry, as the forward reaction goes, the concentration of the reactants gets less and less and less, and so it slows down because there are less, like, reactant particles there to have effective collisions. So the rate slows down. On the other side, the amount of products increase. So you have more and more and more and more products, and as you have more and more products, the reverse reaction starts speeding up. So the forward reaction slows down, the reverse reaction speeds up, and at some point they get equal to each other, and once they're equal, they're locked. Like, one can't outdo the other because they're, like, equal. That is equilibrium. And so we're going to dig into this today, like what is going on, like, at the molecular level. Weirdly, in chemistry class, we're going to talk about what's going on at the atomic level, when forward reactions slow down and reverse reactions speed up, and then they hit this place where they get locked. It's called equilibrium. Yay! So equilibrium. Anytime we say the word equilibrium, what it means is that the forward reaction and the reverse reaction are happening at the same rate. In other words, they're going at the exact same speed. So that way and that way, exactly the same. Got it? I mean, that's all we can say about equilibrium, is that the forward reaction and the reverse reaction are going the exact same speed. You can't say anything else. Like, you can say nothing else about this with, like, assuredness. Well, I shouldn't say that. Maybe there's a few other things we can say. Yeah, there is a few other things. I lied. Or let's just get into it so I can stop unlying here for a minute. So the thing is, equilibrium, it's good to have inside your head. This is like a dynamic process. So if you have a system at equilibrium, right? If you have a forward reaction and a reverse reaction going, and they hit equilibrium, the forward reaction is happening and the reverse reaction is happening, like, right in front of you. Do you understand what I'm saying? But when we look at it, we can't really see it happening, but it's definitely happening. The forward reaction happens and the reverse reaction happens. And it's like if the reactants were red and the products were blue, we would be seeing purple, right? Because red and blue are purple, because it just goes so back and forth so fast that, like, and they're both kind of there because the reactants make products make reactants, all that kind of stuff. And one other, so it's a thing that's constantly happening, even though we may not be able to, like, actually see it with our eyes. Like, the forward reaction is happening, the reverse reaction is happening, stuff is actually happening even though it's so small that we might not be able to see it. The other thing that's kind of clutch here is it has to be in a closed system. Okay, so the thing here is like it has to be closed. In other words, it means that all the reactants and the products have to be held together, because if you have a forward reaction and the products are taken out, then like for whatever reason, like you could scoop it, like reach in and scoop it out, or if the products are bubbles and they like float away, then the products aren't there to collide to make like the reactants again. So the reverse reaction can't happen if you take the products away. So it has to be in a contained unit, so where all the reactants and products are held in the same container, so they can both be available to make the forward and reverse reaction happen. Does that make sense? So if you have a PPT, that's short for precipitate. If a precipitate happens, there can be no equilibrium. The reason being that like once it's a precipitate, it falls out of solution and is no longer in solution to do the forward and reverse reaction. So anytime a precipitate forms, you will not have equilibrium, and also a gas, like bubbles. For bubbles, there is no equilibrium, okay? Because if you have a forward reaction that produces bubbles, the bubbles like bubble up and float away, and then you don't have any products to make effective collisions to make a reverse reaction. So you have to have the products and the reactants stay together, not only in the same container, but like in the same solution. So you can't have a precipitate and you can't have bubbles. You dig? The other thing that we should look at that is like a good thing to like be able to recognize is this little wonderful symbol right. Yeah. So this symbol means equilibrium, right? That is the equilibrium symbol. And it's like, if you can imagine, it's like taking a forward arrow and a reverse arrow and then mashing them up, and you get half of a forward and half of a reverse, because both forward and reverse reactions are happening there. Yeah? So if you see this between this symbol right here, between reactants and products, that means equilibrium. See, it's also, if you look really, really close, it's sneaky. It's got an equal sign in it. Oh! So it literally says, like, it says, wait, let me get a pen here so I can draw. It says the forward reaction and the reverse reaction are equal. Oh man, that's deep, man. That's like some secret hieroglyphic stuff right there or something. I don't know what that is. Da Vinci Code, maybe. I don't know. Anyway, look, here's the thing. This is also another thing about this. When the system is at equilibrium, the concentration remains constant. Okay? It does not mean that it is equal. But when you have something at equilibrium and the forward reaction is going and the reverse reaction is going at the exact same rate, that means every time you make your reactant, you make a product. You make your reactant, you make a product. You make your reactant, you make a product. You make your reactant. So like, the reactants cannot increase or decrease in concentration, and the products cannot increase or decrease in concentration. It does not mean that they're equal. It just means that they're locked. It is like almost always never equal concentration. It means that they're locked, right? So it's usually like you start with a ton of reactants and no products, and it goes and like ends at some weird ratio. But it stays there and it's stuck, because that's what equilibrium means. It is like the forward and reverse reaction are stuck. So they are constant, but they are not necessarily equal. So you should say this over and over. Concentration is constant. Concentration is constant. During a state of equilibrium, concentration is constant. Everybody wants to think, oh, if it's equilibrium, the concentration is equal. That's not true, because look, I'm gonna come back up here. It says right here, it is when the forward and reverse reactions occur at the same rate, right? So it's the speed that is the same. It is not the concentration. Concentrations do stay put, like they are locked in place, but they're not necessarily like equal. Who knows what they are? The concentrations are like kind of all over the place, really. And so what happens is this is also kind of trippy, that reactions have like a fixed ratio of reactants and products. This is weird, but it's like a thing about nature. Like, every chemical reaction will go until it hits a certain like proportion or ratio of reactants and products and just stay at that ratio. It just stays there. It's locked. Because it's made out of two reactions. It's made out of a forward reaction and it's made out of a reverse reaction. And each one of those are separate are separate and unique chemical reactions, and so they each reach their own balance of forward and reverse. Whatever balance that is, it depends on the chemical reaction, and the only way you can know what it is to like experimentally determine it. Now, we have actually experimentally determined it for like almost every single reaction that you could possibly think of, and we've done it like 1,000 million times, and we've measured it, so we can make pretty good predictions about what that ratio is going to look like and how far things are going to go. But it's just good to know, like, we want to lock it in there that like that ratio stays the same. You know what I mean? So here are a couple examples of systems at equilibrium. This is one that will show up. This one actually like shows up a lot. This one, I don't know why. Like a closed. Actually, I do know why. Like a water bottle with a closed lid is actually a very common system at equilibrium because it actually captures. Wow, that's a really nasty looking. Huh? It captures a couple of things about equilibrium, right? Here we have liquid, and here we have water vapor, right? And so that's a system at equilibrium. Like when you close it, the reason why all the water doesn't disappear and evaporate out is because as the water particles evaporate, they're stuck inside there until the water vapor reaches a concentration and is locked. Because as much as particles are evaporating, particles are condensating. And once the gas particles get to a point where there's so much concentration that the condensation equals the rate of evaporation, which is why if you leave a water bottle like out or like with a lid on for a while, you'll see that like little water droplets of condensation will build up on the side, and then that is from the condensation, right? It's evaporating and it's condensating, and as long as the lid is on there, you'll hit a system at equilibrium, which is awesome. Also, another way to think about it is like the traffic between Port Henry and like Ticonderoga, right? There's always people going from Port Henry to Ticonderoga, Port Henry, back and forth for whatever reason, but at the end of the day, it's like the same. So like the amount of traffic that goes down to Ticonderoga is equal to the traffic that comes up to Port Henry. Maybe over the course of a day, but you guys get what I'm saying? Like the populations don't like shift dramatically. It's just like people are just moving around. So the ratios are fixed. It's a closed container. These are just examples. Do you understand what I'm saying? I hope so. I hope I'm explaining it right. If I'm not, call me out on it next time you see me and be like, Stu, you did a bad job on that video. I won't be mad. Oh my gosh, phase equilibrium. Guys, we were just talking about phase equilibrium right? Yeah, this is phase equilibrium. I had no idea. I was so brilliant. It's like clairvoyant. It's like I read my notes ahead of time or something. What are the chances? Honestly, not terribly likely for this guy. Okay, so look, there are a few different kinds of chemical equilibrium. I'm sorry, of equilibrium. There are a few different kinds of equilibrium we are going to look at. The first one is phase equilibrium. Okay, so this is a balance of two phases in a closed container. Like this example that they love to show because it's phase equilibrium is like liquid water and water vapor, right? Like right there. Now again, it has to be in a closed system, right? Like if soon as you take the lid off of that water bottle, you're not going to have a system at equilibrium, because as soon as a particle of water evaporates, it's just going to float up and out and away, and it won't be in the bottle to like condensate to go back into the liquid phase. So it's got to be a closed system. Also, if you have water and ice at exactly 0 degrees, or liquid water and water vapor at exactly 0 degrees, you will have a system at equilibrium as long as the system is closed. You dig? As long as the system is closed. Awesome. So the next one is solution equilibrium. Now, solution equilibrium is equilibrium between like things that are like dissolving. And it's usually only two kinds. It's usually going to be a solid and a liquid. And guys, we're gonna stick with water because it's easy. You can get as crazy and complicated as you want, but let's just stick with water for right now. So it's basically going to be for us gases dissolving in water and solids dissolving in water. Gases, like, I mean, gases dissolve in water. Like there are fish that live in the lake because oxygen dissolves in water, right? And that solids can dissolve in water because we've all put like sugar in our iced tea or something, right? So we know that solids dissolve in water, and we know that gases dissolve in water, but they behave and function very differently, right? So the way that we get gases to dissolve in water are like the opposite way that we get solids to dissolve in water. Okay, awesome. So the two kinds of solution equilibrium. First, we're going to look at gases in a liquid. I'll get my face out of the way for you there. So this is where, gases in a liquid, this is where it is an equilibrium between the gases on the surface and dissolved in the liquid. Does that make sense? Now, there are a couple of things we need to understand. Gases want to go and fly out all over the place, right? Because they're gases. They've got a lot of kinetic energy. There's almost no intermolecular force of attraction. So they just want to fly out all over the place. So to get gases contained and like dissolved down into the water, you literally have to like contain them and smoosh them down, right? So the gases are like, so the first thing you want to do is you want to slow them down. So they're not like all over the place, because that like all over the place is what makes them gases. So what we need to do is we need to decrease the temperature. We need to keep it cold. So you need low temperatures, okay? And what that does, by making it cold, you slow down the gas particles so they're not like flying all over the place. And the other thing you need to do is literally, physically grab them and squeeze them into the water. You need to squeeze them down into the water because remember, gas wants to go. So you do the opposite. You squeeze it down. And the way you squeeze it down is with high pressure. And that literally, physically, it like you can think of it as like shoving the gas particles down into the water. Okay? And so this is like the best way to think about this is like soda. Right? We like if you want to keep soda nice and bubbly, which is dissolved carbon dioxide, you got to keep the lid on it and you got to keep it in the fridge, right? So if you get a brand new 2-liter bottle of soda, right? It is like usually really pressurized. And they do that in the factory to squeeze all that carbon dioxide down into the water, and then they put a lid on it so it stays there. It's a closed system. Carbon dioxide can't escape. So you crack the lid of a soda and poof, right? Well, unless you're careful, you slowly release it. What happens? You hear, right? You hear all that carbon dioxide coming out of the 2-liter bottle, and that drops the pressure on the inside. And as soon as you drop the pressure, those gas particles can fly all over the place, and that's exactly what they do. And they come right out, right? So they come flying out of solution. That's kind of how that do. And also, once you do open your soda, you put the lid back on and you put it in the fridge. And keeping it in the fridge slows down those gas particles so they don't fly out. So the equilibrium between a gas and a liquid, closed container, right? And to make this happen, low temperature increases the solubility of a gas and high pressure increases the solubility of a gas. Now, the other one we have are solids and dissolved in liquids. So this is where we have, this is a little bit more weird. This is equilibrium between dissolving and crystallization, right? So crystallization, I don't know if y'all have ever had the joyous occasion of having those like chunks of sugar at the bottom of your maple syrup. Oh, that's called crystallization. That's because there was so much sugar in the syrup that when you put it in the fridge, it got saturated and the syrup couldn't dissolve any more sugar and it came out, right? And that's what happened. Oh, and I just said this word. I said saturated solution. So a saturated solution is a solution that can't dissolve any more solute. Well, that's a vocab word. So a solute is stuff that's dissolved. Stuff that is dissolved. So for this to happen, the solid and the liquid at equilibrium, first step, you got to have a saturated solution. It has to be. And so what that will look like, and the reason being, is you have to have, all right, there's our container, and here, let's use light blue. Here's our water. See the waves? And here are the little salt crystals. Let's do salt water. Right? So if you add enough water or salt to water that it all dissolves, and then you just keep adding, and you add a little bit more, you'll have a little bit of a salt sitting on the bottom of your cup or glass or whatever it is, right? And so you stir the living daylights out of it. No more salt's going to dissolve. What's happening at the molecular level is, remember, kinetic molecular theory says that stuff is moving around all the time. Molecules are always smashing and crashing and banging into each other. And so eventually one little piece of salt is going to dissolve out. But at the same exact time, another little piece of salt's going to land right up against that crystal, and the crystal is going to grab it and it'll stick. And then another one dissolves out, and then another one precipitates down, and then like another one dissolves out here, and another one precipitates out right there. So what happens is it gets to the point where the dissolving and the crystallizing equal out. At least the rate, the speed at which it can dissolve. Because remember, the more stuff you add, like the more stuff you dissolve, it like slows down. Like at first it dissolves fast, and it dissolves slower and slower and slower because, you know, concentrations change. And then, like I said, forward and reverse reaction. I don't think we need to dig into it too much more, but that's how it works. You have what's called a saturated solution. In other words, it can't dissolve anymore. It's like totally at its max capacity for dissolving. Then you add a couple more crystals. And what happens is one little ion might be floating around, sticks to the crystal because they're ions, and then that makes space for more to dissolve, and then maybe one dissolves from over there, and then another crystal bumps into another ion bumps into the crystal full of ions and sticks, and then makes one more space inside the solution, then one more dissolves over there, and that's how that do. All right, and then the last. This is just the equilibrium between a forward and a reverse reaction. Okay, that's all. And again, there is no observable change, right? We can't see anything happen, right? So, like for this reaction here, we have iron 3+, and in the reactant, and we have iron. This is called iron thiocyanate, and it is over here in the product, and it is in a state of equilibrium. Well, one is the reactant is yellow, the product is red, and what we end up with in the middle is something orange, because we have a little bit of yellow and we have a little bit of red, and when we look at it, we don't see yellow, we don't see red, because they're going back and forth so much. When we look at the test tube, we would see an orange looking test tube. There you go. That's just where chemical equilibrium, that's where the forward and reverse chemical reaction are happening at the exact same rate. And that is it for us. That's awesome. Another Calvin. Who doesn't like Calvin and Hobbes? I love that kid. That kid is hilarious. So to practice this, it's going to be ins and outs of equilibrium, and we'll do that next time I'm looking at you. As always, I super insist that you have an awesome day. Oh yeah, don't forget, like and subscribe down below. This has to go viral. I need to monetize this thing for retirement. Hook a brother up. Have a great day.